So this is a pretty common type of problem that we're going to see. We're going to be asked to find the volumes of shapes that are the result of a rotation around an axis. Now, anytime you rotate a shape around an axis, circles are going to result. So the sphere is just one example of this sort of problem. And when we do this with our circles, our cross sections will always be circles, right? We're spinning around an axis. So we had that pi r squared formula that we used to find the area of the circle. We're going to use that over and over and over again. The only thing we have to remember about this is that the r value is not going to be constant. The radius of these circles is not always going to be the same. The radius of the circle is going to change depending on where on the shape we're looking at. But basically, whenever we have a solid that is rotated around an axis and our cross sections are perpendicular to that axis of symmetry, then we can find the volume by integrating pi r squared. So take a look at this formula. It is just pi r squared times a thickness, right? Remember, this thickness is what's going to add that new dimension, right? Pi r squared finds an area, and then the dx adds that third dimension, and then we're going to integrate that. We're going to add up all of our cross-section volumes from the far left to the far right. So number one thing to do in these sorts of problems, always, always, always draw yourself a picture of the two-dimensional region before you start. Okay, so in this particular example, we've got a region bounded by the x-axis, and the curve y equals the square root of x, and the line x equals 1. So these are all very basic things to be able to graph. Of course, the x-axis is easy. The x-axis is right here. Okay, it goes both directions. Yeah, I don't even want that there. And we will graph y equals the square root of x. That starts at the origin and curves like that. Notice that I'm just doing a rough sketch. I know the basic shape, so I'm just going to draw that. And then x equals 1 is going to be a vertical line. Let's call it x equals 1 right here. That's the vertical line. Okay? So it should be very easy to come up with a sketch of this region that's bounded by the x-axis, the curve square root of x, and the line x equals 1. So this region, we could find the area of this. That's the old school thing that we've been doing with these regions. Now what we're going to do is we're going to take this region and we're going to rotate it around the x-axis. So take a look at what happens. We're going to go, whoa, around that x-axis. And this thing is going to flip around so that we've got this kind of parabolic bowl, right? We've got a top half and a bottom half. And each one of those cross sections is going to be a circle, right? So we're going to take one of those Riemann-summed rectangles and we're going to spin it around, and that's going to create a disk. So Corpy likes to say perpendicular. It's kind of a pun because the cross-section is perpendicular to the axis of symmetry. So when you have that, you're going to get a disk. So perpendicular, that kind of helps you remember. So notice that this particular disk is smaller than the biggest one, right? But it starts out itty-bitty tiny 0, and then it gets bigger and bigger and bigger as x increases from x equals 0 all the way to x equals 1. So that radius of our cross-section is found by, well, it's right here, right? It's the top minus the bottom. It's the height of this rectangle that we've been finding for areas. So it's the top minus the bottom. Top minus, whoops, you don't have to spell out the word minus. Top minus bottom, in this case, that's the square root of x is the top curve, and the bottom is 0. Y equals the square root of x, and y equals 0 are the top and the bottom of our radius. All right, so that's our radius function. So now we can just find the volume by integrating from our starting x value of 0 and ending at our last x value, our rightmost x value of 1, and we're going to integrate the area of the circle, pi r squared. Now remember, you can factor out the pi, it's a constant. You don't have to, but it's nice to. And then we've got our radius, which is the square root of x. And we're going to square that, pi r squared. Don't forget the dx. That's going to give us that third dimension. And this becomes a very straightforward integral. We're going to do the integral of x. Well, that's easy, right? We've got 1/2 x squared. We'll evaluate that at 1 and at 0, and then subtract the 2. So we've got 1/2 pi, or pi over 2, times 1 squared minus 0 squared, or just 1. So the final volume of this parabolic bowl is pi over 2. Pi over 2 cubic units, whatever those units happen to be. If these are measured in feet, then this is a cubic foot, right? Or pi over 2 cubic feet. So that's a nice volume problem for us to consider. It's not going to be directly related to any formulas that we learned in geometry, but that's the beauty of calculus, is we can generalize this to all sorts of different shapes. So that's your perpendicular method. So let's try another one. And what's going to happen on this one? Well, let's take a look. We still have a region. Oops, forgot to axisify my mouse. There's the axis. So we still have a region that we can graph. We've got the line y equals 1. Y equals 1. The same curve, y equals the square root of x. And we've got x equals 0. Well, that's the y-axis. So that's right here. So if we look at just those three curves, this is x equals 0. This region that's bounded, this triangular-ish shape right here, is being revolved. This time it's being revolved around the line y equals 1. So take a look at what's going on here. We're going to take this rectangular region right here and revolve it. Let's use that orange again. Revolve it around the line y equals 1. So we've got ourselves discs, right? This is going to be some sort of, let's go back to green. And, if we look at this, it's going to be some sort of like cone with curved walls when we rotate it, if you can imagine that. So the radius here, the radius function is, again, changing. Notice that the top of this radius is the red line, y equals 1. And then the bottom of this radius is the curve, the square root of x. Okay, so if we were going to find the area of this shaded yellow region, we would integrate this from an x value of 0 to an x value of, well, it didn't tell us what the x value was. But we know it's 1, right? If y equals 1, then x equals 1. So we're going to integrate from 0 to 1. That would find the area of that yellow region. But now we're going to say, well, this is actually not a rectangle. This is a radius that we're going to revolve. So we're going to do the pi r squared business again. So we're going to do the integral, the volume equals pi times the integral from, again, 0 to 1. Our radius squared is going to be 1 minus root x that we're going to square. And that's going to be a little bit harder. We're going to need to expand that out, right? We'll take 1 minus 2 root x plus x, and that's going to be our integrand. So we can integrate that. We're going to get x. We're going to get minus, well, we've got a minus 2. X to the 1/2 changes to x to the 3/2. And we'll divide by 3/2, multiplying by 2/3. And then we have that 1/2 x squared. Okay, so that integral is a little bit more complicated, but I think we can deal with that. So we've got pi times that antiderivative evaluated at 1. So that's 1 minus 4/3 plus 1/2. And we're going to subtract, well, 0 minus 0 plus 0, so we can ignore that part. So when we get our common denominator, we get a 6 over 6 minus 8 over 6 plus 3 over 6, which is equal to 1 over 6. So that's going to work out to be pi times 1/6, or pi over 6. And that would be the volume of that coney sort of shape that we've got right here. A nice little exercise might be, well, we would expect that this answer to be close to the volume of a cone whose radius is, well, this radius is 1. and whose height is 1, right? That distance right here, this is the height of 1 as well. So play around with this. The volume of a cone is 1/3 pi r squared h. Well, r and h are both equal to 1, so we're going to get pi over 3, which is bigger than pi over 6. But they're kind of in the same ballpark, so I could be convinced that, that this answer is right based on the fact that this is similar but bigger. Okay, so it's often nice to kind of ask that question, does my answer make sense? And let's see if we can do this one more example for the section, for the perpendicular section. This time we're changing the functions up. This time we have a cubic. We'll go ahead and graph that two-dimensional shape first before we start revolving it around the y-axis in this case. So that's too far. I don't want to spoil example 5 for anyone. That's coming up later. So let's get a quick graph here. We've got y equals x cubed. That looks like this. Y equals x cubed. Notice that we don't really need to spend a whole lot of time making these graphs. We just need a basic shape. Y equals 8. I think we know that y equals 8 when x equals 2. So that might be a useful thing to find, right? 2 cubed equals 8. X equals 0 is the x-axis. And this is a new one, right? Because this time we're revolving around not a horizontal line, but a vertical line. So if our cross-section is perpendicular to the axis of revolution, then we better draw a horizontal rectangle instead. So this is going to spin around this way, and we're going to get some sort of bowl like that, kind of a right side up bowl. So the important thing to remember here is now that little thickness, that thickness is no longer a dx, this is now a dy. So we're dealing with a y problem here. We want to know what the radius of the disks are, not as a function of x, but as a function of y. So when we did this before with the area, we remembered, oh, well, if we're going to integrate with respect to y, then we don't do top minus bottom. We do big minus small is now right minus left. So that's an important thing to remember, right minus left. So in this case, the right value is the curve y equals x cubed. In other words, x equals the cube root of y. We want an x value written in terms of y. And then the left value is x equals 0, right? X equals 0, so that's easy. So we'll just use y to the 1/3. The radius function of y is y to the 1/3. So we're going to integrate. The volume is pi times the integral of r cubed, so y to the 1/3. I said cubed, I meant squared, pi r squared, dy. Now don't go from 0 to 2, right? X equals 0 to x equals 2 is not good because we're not stacking these from left to right. We're stacking these from bottom to top. So we're going from y equals 0 to y equals 8. So be very careful with that. This tells us the values of these numbers, right? Or the type of number where we put here. We put y values here because we're integrating with respect to y. So this should be pretty easy, right? Y to the 2/3 integrates to y to the 5/3. Add 1 to the exponent. Make sure you multiply by that, reciprocal. And then we still have the pi. We'll evaluate that at 8, and we'll evaluate that at 0. So the 3 pi over 5 gets factored out. We'll take 8 raised to the 5/3 minus 0 raised to the 5/3. Well, take the cube root first, right? Don't take 8 to the 5th power. Take the cube root first and get 2. 2 to the 5th is 32 minus 0. So we end up with 96 pi over 5 is the answer to the volume of that right side up bowl that we create over here when we rotate this shape around the y-axis.